So LeetCode number 99, recover binary search tree. For this problem, we're giving a binary search tree with two values swapped, and we need to recover it so that it is back again to a valid binary search tree. And just to be clear, we're not going to be solving the follow-up because that's a whole another video. Okay, so to solve this, we're going to think about what it means that two values are swapped. That means that when we run the in-order traversal of the invalid binary search tree, we're not going to get an ascending list of values. Like usually when you run a in-order traversal on a binary search tree, you get an ascending list of values. For example, if we run it on here, we get 1, then 2, then 3, and then 4, right? So that would be an ascending list of values for an in-order traversal of a valid binary search tree. But since two values are swapped, what's going to happen is we're going to get something like 1, 3, 2, 4, which is not an ascending list of values. So yeah, what we're going to do is we're going to run a in-order traversal of our tree, of our binary search tree, invalid binary search tree, and that is going to allow us to check when we have nodes that are not in order, like they're not ascending, and that's going to tell us which nodes we need to swap. Okay, so I'm laying down the code, the framework code for this problem, and then we're going to do the actual business in the in-order traversal. So we're going to have to keep track of the two nodes of which we need to swap the values. So those are going to be two elements, three nodes. And then we're going to also keep track of the previous element in our current in-order traversal. So we're going to run the in-order traversal, but instead of pushing all of the values to an array, we don't have to do that because we're actually only ever going to look at the last value that our in-order traversal went through. So instead of keeping all of them in an array and then looking at only the last value, you can literally just store the last value, right? So that's going to be your previous element. And we're going to have to take a look later on at why it's initialized with -infinity. Okay, so then what you do is you call your in-order traversal function on your root, and then we're going to have to implement this. But basically, this is going to be just a normal in-order traversal of the tree with the addition of keeping always track of your previous element instead of pushing the values to an array, and also finding the first and second element of which you need to swap the values. And then we are actually going to do the swapping. So the first element value becomes the second element's value, and the second element's value becomes the first element value. So now all that's left is to implement the in-order function, and keep in mind this is just a completely normal in-order traversal of the tree, just with some modifications. So the first modification is that we're going to have to keep track of the last element that we visited at all times, right? So that's the first thing that we need to change about the common in-order traversal. So instead of pushing the values to an array, we just keep track of the last one. And then we're going to also have to check if there are any invalid nodes, so like nodes that have a value that is smaller than the previous value. Those are going to be our invalid nodes, which we're going to put in first and second element so that we can then swap the values. Okay, so yeah, here we go. Here's the in-order traversal function. First of all, your base case, then you call on the left subtree, then you keep track of the previous element of your last element that you visited, which is the current one, and then you call it on the right subtree. And yeah, so that's the framework for a common in-order traversal. And now all that's left is to actually find the first and second element of which we need to swap the values. So here's the thing. If you were in a valid binary search tree, this condition would never happen. You would never have a previous element of which its value is greater than your current element because you're in a binary search tree. So you would always have an increasing, like your current node would always be greater than your previous node. But here, since two values are swapped, it could happen that the previous element's value is greater than your current one. And what that tells you then is that you're definitely currently on the elements that you need to swap. So I'm going to give you two options and that do the same thing but are written differently, so you might want to look at both of them and decide which one you prefer. So here's one option, and here's also the second option. So these two codes do the same thing. So maybe looking at this one is easier to understand at first maybe, but this one is shorter and you might prefer this one. So yeah, I've put both of them. You can decide which one you want. So essentially what you're doing here, so let's look at this one before. So you're checking if you've already assigned something to the first element that you need to swap. And if you didn't, so it's still null, meaning that you haven't assigned anything to him. And the second condition is that we do have that mistake, we do have the previous element value being greater than the current element's value, which should never happen. Then if those two conditions are met, then you assign to your first element the previous element. And we can run an example for that. So here we would have something like 3, then 2, then 1. So when you go from 3 to 2, you find that your current value is smaller than the previous value, and you find that first element is null, and so you assign to first element 3, right? So now 3 is your previous element. And then you go through the second condition and you check, is the first element not null? So maybe you've already assigned something to it. Like in this example, we have already assigned 3. And if the previous element's value is greater than the root value, so you have a mistake there, you have an invalid sequence there, then you assign to the second element the root. And the reason for which you need to do this, even though like right now this is going to be done, so you're going to assign to the second element the tree node with value 2. So that's a mistake, but it doesn't matter because it's going to get fixed when we get back up. So for example, here now we would go to 1, right? It would be the next node in the in-order traversal. And we would see that the previous value is greater than the root value. And we already have a first element. So we're going to go down this path again. And we're going to overwrite the second element, which was not the correct second element over which we need to do the swap. And now we're going to overwrite it with the correct value that we need to make the swap. And so, yeah, this is working, but I find it's much more concise to do it this way. So yeah, you decide I'm going to leave this in. And you might be asking why, like if this is getting overwritten anyway, then why don't you just put an else here so that this doesn't run in the first time? Well, I can't put an else here because it could be, like it is not guaranteed that that is not the element that you want to swap. It is not given. It might be that there is another element that you want to override the second elements with, but it's not a given. So you can't just put an else here, otherwise the solution is not going to work. Because it could be, you see, it doesn't work. It could be that on the first try, you do need to set the second element to the current roots node, and there the swap works and the solution actually works. So yeah, the time complexity here is O of n because you go through all of the nodes once, and the space complexity could actually be O of n if you have a unbalanced binary search tree. So yeah, that's it. It was a pretty hard problem to explain, and let me know if you want me to also do the follow-up problem where you do it in O of 1 space. But that's a pretty hard. You should just know by heart the Morris traversal of a binary search tree, which I guess is really a obscure algorithm. Not many people know it. So yeah, that's going to be it from me for this problem for now. So thank you for watching, and bye.